thanks, Yanting, for the very nice introduction. What we are watching here is the formation of a cluster, in fact. So it's the formation of a cluster which will be about 10 to the 14 at redshift 0, so a small Virgo-like guy. And it's kind of an unusual view. The color shows you gas velocity, actually. I'm gonna rewind again, just one more time. So in the upper right corner, you see redshift, already past reionization. We're looking at gas velocity in a high redshift. This is a proto-cluster environment, right? What you see is rapid accretion. You see these inflows from the cosmic web coming into a dark matter halo. This is about a megaparsec across. Until at some point on redshift 3, redshift 2.5, you see this onset of this very strong kind of bipolar collimated outflows being launched away from the galaxy at the center of the halo. This is the onset of strong AGN feedback and the start of the quenching of this massive galaxy so that it can eventually, of course, become a quiescent central galaxy of a massive cluster. You see, of course, another guy over here on the right. You know, the central galaxy is disk-like, it's kind of edge on, it's launching these fast outflows from the AGN. And you see all the orbiting substructure, right? Galaxies, their tails being ram pressure stripped, flowing through this environment and building up this halo. As we pass redshift 1 or so, the view switches, so now we're looking at the stellar mass density. And really, I love this part. It's just a perfect example of a hierarchical structure formation. Right? We see a central big guy down here and another one coming in. These two will have a binary merger near redshift 0. But you see hundreds, thousands of satellite galaxies passing through this environment and getting morphologically transformed as they do so, right? The spirals getting stretched out, stars getting thrown into the diffuse stellar halo, as we heard about a lot today, forming these really beautiful shell-like, stream-like, fine-grained features of the intercluster light until we reach redshift 0. So I have a few movies. Movies are fun and a simulation talk. So today I'm very excited to tell you a bit about how we simulate galaxies on the supercomputer. So the official title is Cosmological Hydrodynamical Simulations from Galaxies to Clusters. And let me thank, again, Yanting and all the organizers for an amazing workshop so far. So this is a bit of a longer talk, so I'm going to start a bit gently with an introduction. Of course, when we look at galaxies in the real universe, and this is a light cone, so the observer sits here, distance away from us, position on the sky, we see the galaxies are not homogeneously distributed. Of course, they're clustering. They formed what we call the cosmic web of structure. And for about 25 years now, we've been able to reproduce that large-scale structure of the universe on the computer, right, with gravity-only calculations. So this on the bottom is a numerical simulation. This is the Millennium simulation from 2005. It's ancient nowadays compared to the 2DF, which is also an ancient redshift survey. But what I like to say about this image is that each one of these dots, right, is not just a point particle in space, but it's a real galaxy. Real galaxies are really cool. In particular, they're super complicated, right? So they come in this huge diversity of properties. So this is a Hubble tuning fork-like diagram from Spitzer, I believe, in the infrared. So there's spirals, things with bars, there's irregulars, there's boring ellipticals, some boring ellipticals. And they come in a huge diversity of shape, sizes, color, star formation activities, and on and on and on. And then they also undergo these spectacular transformations, right, throughout their lifetime. These are galaxy-galaxy major mergers from Hubble. And so our goal is really to try to explain, right, with the theoretical models, the diversity of the galaxy population that we see when we look out on the sky. And so we like to phrase it sometimes as creating universes in a box. So the box is literally a cube, and that's what we simulate on a computer. And so our goal is, working generally within LAMCM, we like it, is to develop a comprehensive theory for galaxy formation. And what that means is a numerical framework plus a physical model that explains how galaxies form and how they evolve. And we want to do that across the entire mass scale of objects, all the way from dwarf galaxies up to galaxy clusters, of course, the topic of this week. And we like to do that across all of cosmic time, from beyond reionization all the way down to redshift 0. And the best tool, at least from my point of view, are cosmological hydrodynamical simulations. So cosmological, of course, means that we're starting with initial conditions motivated by lambda CDM, motivated by the CMB. And additionally, it typically means we're running large representative volumes. So we're not simulating one galaxy in particular, but thousands or millions of galaxies and how they interact and co-evolve. And hydrodynamical, of course, means not just n-body or gravity-only simulations like Millennium from 2005, but we're also trying to simulate the gas, which also means the stars and all of the messy kind of baryon physics which comes along for the ride. Okay, so that gives us a lot of information in these kinds of simulations. But these are not just catalogs of galaxies, right? They also really are rich in terms of spatially resolved information of the different matter components of the universe. So this is about 100 megaparsec a slice from top to bottom through one of these simulations. This is dark matter density on the left. Right? This is gas density, so tracing dark matter, of course, on large scales. This is gas velocity, so the fight against accretion versus ejection from feedback. We also know, of course, where the stars forms. This is stellar density, the thermodynamics of the gas, so heating to structure collapse, but also feedback. We know, of course, that the stars are synthesizing heavy elements and they're ejecting these metals back into the interstellar medium, circumgalactic medium, and intergalactic medium, polluting the universe with metals. This is the metallicity field. This is an on-the-fly shock finder identifying shocks at the edges of cosmic web filaments and surrounding halos. These simulations are nowadays starting to include magnetic fields, so this is the magnetic field strength as it's been amplified down to redshift 0. And of course, we get access to lots and lots of observables. This is X-ray emission on the far right, as would be emitted by the hot plasma in the intergalactic medium and in clusters. So, which is to say that these modern hydrodynamical simulations give us lots and lots of information that can make connections to a whole diversity of observational regimes, which is why they're really fun. The other thing I like to point out in this image is that galaxies are super small, right? They're basically within a single pixel of this image would be a dark matter halo. We have to zoom in here by a factor of 10,000 or so to see a galaxy. And if we do that, these are what galaxies look like, right? So these are stellar-like mocks from TG50. They've been run through a dust radiative transfer code, so that's why you get these cool obscuration effects. You get these dust lanes when the galaxies come edge on. So these are just some beautiful redshift 0 examples. So there's a whole diversity, right? All the way from kind of spheroids to mergers in action to really thin disks, things with bars, nuclear bars in the center, warps. So really a diversity of the population. And again, not just trying to simulate one or two galaxies, but lots and lots and lots. So I'd like to flip to this slide. It's the 1,000 most massive galaxies from one of these simulations at redshift 0. Okay, I'm going to show you another movie. So let's zoom in. Let's look at how a galaxy actually forms in a simulation like a lustrous TNG. So we're watching the formation of a single galaxy. This is about the dark matter halo scale, the virial radius. And this will be a Milky Way at redshift 0. Right? So this is a kind of a typical disk galaxy formation. But at redshift 3, 4, there's no galaxy here at all, right? It's just this turbulent, messy ball of gas and accretion coming in, forming kind of this turbulent reservoir of star-forming gas at high redshift. This is what we think high redshift galaxy formation may look like. But at some point, we pass redshift 2, and you start to get a sense that things are settling down. Right? You start to see what looks like a disk emerging. It's kind of edge on in the gas, and this is a zoom into the stars. Because the gas has settled down into a rotationally supported structure and started to form a disk galaxy. It gets bombarded by mergers every once in a while. And we saw a minor merger come in there and actually torque the disk and start the formation of this little bar, which will keep rotating around and spinning until redshift 0. And the other thing you see nicely in this movie is the baryon cycle, right? It's the competition between gas coming in and gas getting blown out. You can see it here. All this gas getting ejected from stellar feedback. These are all supernova-driven galactic winds leaving this galaxy. Some of them are turning around quite rapidly. We call these recycling or fountain flows, gas reaccretion, taking place basically within the dark matter halo. And as this movie ends, redshift 0, it kind of looks something like a Milky Way. Okay, so one of the fun things we can do with simulations like this is we can, of course, interpret observations, and we can look at particular classes of objects, particular phenomena, and try to say, how did that come to be? How did that happen according to the model? So we can look at galaxy mergers, for example. These are real cases, and we can go find analogs. into simulations, right? We can find systems which look like this, and then we can use them as the time machine. We can go backwards and we can ask, how did these mergers occur? What processes were dominant? Here's M104 to Sombrero Galaxy, and 5 kind of things from a simulation which look similar. We can understand particular stellar morphologies, but not just stellar morphologies. Here's another example. So in the center of our own Milky Way, we observe the Fermi bubbles, now the Iwasita bubbles. So very strong outflows driven from the center of our galaxy. And when we look at TNG50, we put galaxies edge on, we look at the X-ray emission, we see qualitatively similar kind of morphological features. They're just there. And in the simulation, we know that these features are driven by AGN feedback, for example. So we can start to at least have an explanation of some phenomena that we see. Here's another example. So gas jellyfish galaxies, we heard about these yesterday, and analogs from the simulation, right? Just looking at satellites in groups and clusters and looking for galaxies with strong signatures of wind pressure stripping and tails of gas. We're finally moving to the more massive regime, again, stellar halos and intercluster light, right? An observed example, and shells and streams are just common byproducts of assembly. You always see them when you start to look at the stellar structure of halos. Okay, and I want to emphasize a point in the rest of this talk, which is that actually this connection between galaxies and their halos, I think, is quite important to the picture of what's going on. We ask kind of the most fundamental questions about galaxy evolution. For example, why does the galaxy stellar mass function, so just the histogram of galaxies of different stellar masses, and why does it have this shape? Why does it have the shape that it does with the knee and the rarity of the massive object? Or we ask, why does the distribution of galaxy colors, why is it bimodal, as we see in Sloan? Why are these two distinct red and blue populations? And I think a big part of the answer to these kinds of fundamental questions is that gas accretes into these dark matter halos. We have inflows. This builds the gaseous halos, which of course fill the dark matter halos. This gas cools and forms the galaxy, right? Provides the fuel for star formation, and then this, of course, leads to supernova explosions, black hole formation, AGN feedback, and produces outflows and winds such that this kind of cycle can start again. And this, many people would call this the baryon cycle, and it takes place in the gaseous halos of galaxies and in the intercluster medium of clusters. But unfortunately, simulating that process is extremely hard. And there's 2 challenges, really. So the first is the challenge of scales. And I like to show that with this image. It starts to zoom in from the large-scale structure of the universe and gigaparsec scales where things are homogeneous, isotropic, down to megaparsec scales of an individual cluster, an individual dark matter halo. But you have to zoom in down to kiloparsec scales, to find a galaxy. And unfortunately, you have to zoom in by another factor of 1 million or so to start to access the scales where really important astrophysics happens. And the problem is it's not just collapse, it's not just information flowing from large scales to small scales. There's this back reaction, and the jets launched by supermassive black holes are a perfect example. Right? So we know that these relativistic jets launched from really sub-parsec scales can influence the entire atmospheres of galaxy clusters, a factor of 1 billion larger. Capturing that on the computer is tough. The other challenge is just the physics. So if I start to list, the laundry list of physical processes that we would like to include, starting from the gravity and the hydrodynamics, the 2 most important, down to processes maybe important in galaxy clusters, like cosmic rays or complicated plasma physics. A lot of this is tricky to put on a computer. So we try to do that, and when we try to do that, we have to really combine a numerical code and a physical model. So this slide is a bit detailed. It's kind of for the simulation aficionado, so close your eyes if you want. Right? So we're using typically this AREPO code. We're solving the equations of self-gravity coupled to magnetohydrodynamics. And this code is fast and it's accurate. That's why we like it. On top of that, we start to build our physics, right? So we start to build a model like we would call the illustrious TNG, a physics model. So it includes gas, microprocesses, chemistry, cooling, of course, star formation, stellar feedback, stellar evolution, the production of heavy elements, supernova feedback, stellar feedback channels, and then, of course, supermassive black holes, how they form, how they merge, how they accrete gas, how they release energy. Right, so we put all this soup together, and that is something that we call the illustrious TNG model. Okay. Models like this are used to run these cosmological hydrodynamic simulations, right? And they all have this common goal, right? So all of them are trying to solve for the simultaneous coevolution of cold dark matter, gas, stars, supermassive black holes, sometimes magnetic fields, sometimes radiation, sometimes cosmic rays. New kids on the block. And of course, one of the projects that I've been most involved in is the illustrious TNG series of simulations. So originally started with these three, where TNG50 is the highest resolution, right? TNG300 was the largest, and we recently added this new project, TNG Cluster. But these are not the only games in town, right? You've heard a lot, different names of these types of simulations from the last 10 years, Magneticum, Eagle, Horizon AGN, Simba. Then there's a whole class of simulations, right, focused on larger volumes, I would say, often with more cosmology-oriented focus. For example, the new Flamingo simulations, very, very large. And then there's projects focused on high resolution, for example, TG50, the New Horizon simulation, Firebox, Colibri. These are focused more on small scale, right, pushing towards the galaxy formation physics. And in particular, I want to talk a bit about TNG Cluster, right, for the rest of this talk. So TNG Cluster is a suite of about 350 massive galaxy clusters. You see a picture of it here. Right, so these come from a gigaparsec volume. It's very large, but we didn't simulate the entire volume. That would be impossible at this resolution. So instead what we did is we selected lots of clusters at random. We simulated them individually, and then we kind of stitched them back together. We put them back where they belong to form kind of a virtual simulation. So this is a project led by myself, together with Annalisa Filipic in Heidelberg, and it is a simulation of clusters, including that fiducial kind of illustrious TNG physics model that I just described. I want to give you a bit of a landscape of these kinds of simulations of clusters and start to just give you a sense, a comparison, right? So this is a plane, a resolution of the simulations. Going up is better, lower mass resolution. And on the bottom we have number of really massive objects. So this is similar to volume. So going to the right is better. And our challenge is thus to go into this upper right-hand corner. So this is made in a way which TNG Cluster looks very good, of course, by selecting in particular the most massive objects. But you see there's kind of this threshold. It's very hard to go up here. Down here we have like these are the Magneticum boxes, for example. Here are some of the Flamingo boxes. Here's 300 project, we heard about it. So a lot of these sacrifice a bit of resolution, right? They're lower resolution, but they gain in statistics very fast. They might have very, very large samples. And on the other hand, the only simulation really even higher resolution of clusters, these are very rare. They're very hard to do. This is still the Sea Eagle hydrangea simulation that we also heard a bit about. So TNG Cluster is kind of a compromise, right? Quite good resolution for the kind of statistics, a few hundred massive halos. So that was our objective. This is a table of numbers. Again, if you don't like tables of numbers, just kind of close your eyes. It's comparing the three TNG simulations to TNG Cluster. It has some very simple messages. So the first is that it's very big. So that the box volume is very large, gigaparsec, the number of particles you need is very large. Right? But the resolution is exactly the same as what we had before. And the resolution, if you like a number to keep in mind, we often think about this, the mass of the baryon. So a single gas cell or a single star particle has to have a mass of 10 to the 7 solar masses. And that's how much mass a star has to represent. If it's more intuitive sometimes to think about the resolution in space. We try to have a number about 1 kiloparsec. That's a characteristic resolution number you can keep in your mind for these types of simulations. And finally, of course, we have the sample. The goal of this, previously we had maybe 3 halos above 15.0, very kind of sparse sampling, and now we have 90, right? So really good statistics to see the kind of cosmological variation of clusters and how they work. Okay, so this is what the mass function looks like. It's simply a histogram, right? Number of halos is a function of halo mass in 0.1 dex bins. You see there's about 70 or 80 halos for every 0.1 dex of M200C. So the red is TNG300, right? That's what volume limited statistics in a 300 megaparsecs volume looks like. You have lots of small clusters, of course, but very few of the big guys. So the goal with TNG Cluster, which is shown in blue, is to kind of fill in this gap. to have a complete sampling of the gigaparsec volume above 15.0, then to kind of make this distribution go flat so we have plenty of statistics to look at clusters across the mass range. I also like to show it in this plane. We've seen this also during the conference. So this is halo mass as a function of redshift. This is a maze of dots, right? These are all observed clusters, in fact. So there's some X-ray samples, some SZ samples, maybe some optical samples a bit out of date. Giving you a sense of where the observational landscape is, right? Where clusters are seen with some of our favorite friends like the Bullet cluster, or Coma, or Virgo down there at low mass. So in TG300, right, we had this kind of sampling of this space. So each line is a cluster redshift 0, and then it goes back in time showing you the progenitor, right? The mass assembly history of that cluster. But really too sparse to talk about the most massive halos, and that's the goal of TG cluster, again, just to fill in the really high mass and to let us explore the most massive structures in the universe. Okay, so that gives us, again, the statistics to look at the diversity, right, and what's going on. These are X-ray emission maps on the scale of R200. Those are the white circles. Just the first 60 clusters kind of chosen at random. Some are extremely boring, right? Some are kind of spherically symmetric blobs of X-ray emission, but some have lots and lots of substructure, ongoing mergers, double mergers, quintuple mergers. So lots of diversity across the population. But still, by keeping the high resolution, that lets us zoom in. Right? So it lets us zoom into an individual cluster and see detailed kind of substructure in the X-ray. We see little cavities, maybe. I'll come back to this, related to the AGN feedback. We see, of course, the satellite galaxies, even with their tails as they're falling into this. We see kind of fluid instabilities developing in the intercluster medium plasma. And again, this is the X-ray emission, but there's a lot of different kind of information content about each of these structures, right? Of course, also the dark matter, the CDM, stars, where they form. We can do observables like TSZ, metallicity and magnetic fields that have been amplified, and cold gas content. This is the H1 column density in this same cluster. Okay, so what does all that information let us do? It lets us verify, let's just check. First of all, are these simulations realistic at all? Let's compare to some data. We can compare to something very classic like the X-ray scaling relations. Right? So this is just X-ray luminosity within R500, soft band as a function of M500. So here again we see T300 put together with TNT cluster, it forms this cluster of points, and we can throw on top some data from observations and say, okay, it's in the ballpark. Nothing is crazy. Just a kind of zeroth order validation of the model, of the illustrative TNG model, realized in these very high mass halos where we never really knew what it would do before. Okay, what else can we do with these simulations? We can make movies, of course. So one more movie. This movie is for Yen Ting, that's right, because we're going to watch again the formation of a cluster. This is a very big cluster, so 2 times 10 to 15 by redshift 0. Let me pause it. Let me pause it. Because this movie is filled in the bottom left with lots of numbers. And what we want to look at here is the star formation rate of the protocluster. Right? We're wondering, so here's redshift 6, if at some redshift we reach really high kind of SMG-like star formation rates. I think I saw 1,000 go by. I think I saw, as I recall, I want to find 3.7, I remember. We had a really good number. 1,400. There was even I saw 2,400 solar masses per year. So this is a booming, ultra fast assembly of galaxies at high redshift, right? So, high redshift universe is a really rapid place. Very high star formation rates in the progenitors of these protoclusters. So this is gas density, the main view you're seeing here. This epoch was here when the black hole was actually at its highest accretion rate. This is the black hole accretion rate versus time. We switched the view here to look at the gas temperature now. So yellow is simply the very, very hot gas. You see that the hot plasma is very dynamic. It's moving all over the place. It's constantly being bombarded by big mergers. Look at this. Merger-driven shock going out to enormous scales beyond the R500, R200. I'm sure the 2 circles is cool, like Kelvin Helmholtz instability and the swirl of the gas as the merger progresses. Then we come back to redshift 0, we switch the view again back to gas density where things are calmer. And you see just this main structure surrounded by just all the other neighbors and substructure. But of course, inside the gas, all the stars have formed. The BCG, but the satellite population is really thousands of little galaxies surrounding such a big halo. And then we're also, in these simulations, running this shock finder. So these are identified shock surfaces in the gas, right? Tracing the combination of merger and accretion shocks, but also feedback-driven shocks. The first are going in, the latter are going out. Okay, I want to touch on a few highlights from the simulations. Maybe I have 15 minutes or so. I'll start with cold gas, because we've talked a little bit about cold gas and galaxy clusters. And there's actually there's actually a lot. So the top is cool gas, the middle is warm gas, the bottom is hot gas. So on the left you have fractions of the total, on the right you have just total amount of mass in solar masses. That's a function of halo mass. These are all halos. The clusters are here just on the very right side, right? So obviously by mass fraction, we're dominated by the hot. And by fraction, of course, the cold is an insignificant component. But in terms of the amount of total mass, of course, clusters have more cold mass than any other halo. They have a ton. This is seen observationally, for example, in alpha H1 stacking results. These are these white symbols. So this is H1, total H1 mass, and a halo is a function of halo mass across the cluster regime. So these halos can have 10 to the 11, 11.5 solar masses just in kind of 10 to the 4 Kelvin neutral hydrogen floating around. It's not what you usually think about when you think about the baryonic content of clusters. Okay, this is redshift 0, and indeed at redshift 0 things are a little bit boring. Okay, so this is kind of a quiz. These are 3 pictures, 3 clusters: low mass, intermediate mass, high mass, on the scale of R200. You guys see the little purple dots? So what are they? I'm talking about cold gas. They're the cold gas. There's not much there. It's a bit boring, redshift 0. You start to look at the protoclusters, and these things are filled with enormous amounts of cool gas. We were discussing, of course, that high redshift, this is redshift 0.5, redshift 2, and redshift 4, the leftmost panel, where in fact the baryon budget is predominantly, if not the hot virialized gas yet, it's the cooler phases. I mean, you can't observe these things at redshift 4 in X-ray or the SZ, fine, but you could see them, of course, in something like Lyman alpha. We haven't talked much about Lyman alpha. This is, in fact, a Lyman alpha emission at redshift 3 from one of the progenitors of one of these TNT clusters. So this is work from Chris Byroll, a postdoc in the group. And what you see is this structure. Some people would call them Lyman alpha blobs. Some would call them giant Lyman alpha nebulae. Hundreds of kiloparsecs in extent, extending down to surface brightness 10 to the minus 19. That's kind of an observable level, this white contour. And inside this blob of Lyman alpha emission, it's filled with galaxies. Those are the red stars, and accreting AGN. Those are the purple hexagons, blue hexagons, all of which emit Lyman alpha, which then resonantly scatters off the gas and lights up this structure. So Chris has developed a code to follow that scattering process of Lyman alpha photons. Okay, let's think about the optical a bit. So let's think about the progenitor galaxies which actually build the cluster itself. So again, we have 5 examples of low mass clusters, intermediate mass clusters, high mass clusters. Those are the 3 rows. This is all redshift 3. So we've gone back to redshift 3. That's where are all the progenitors. And the color in the background you see are smooth density maps of the galaxy members. And in the red markers, you see some different indications. So the center mass is the red X. We have the highest peak in the galaxy density map. That's the bigger X. We have the most massive galaxy in the field. That's the square. We have the actual progenitor. There's only one. The actual progenitor of the BCG, that's the star. So sometimes they're all in the same place. Okay, the center is clear where this protocluster is, but at other times they're really not. Right? It's really hard to define not only how big such a thing is, but also where its center really is. And we can use the simulations, we can start to quantify this. We can ask what is the separation between the peak of the galaxy density and say the most massive galaxy or the actual progenitor, or observational samples limited to say stellar masses you could observe or star formation rates you could actually observe for different stellar mass bins as a function of redshift, right? So these things have separations which get quite large at high redshift, it becomes quite hard to identify and actually where the protocluster might be. But we can use the simulations, right, to quantify and perhaps optimize the selection choices, right, how to find such things. Let's go back to redshift 0 and talk about star formation activity in the central galaxies of clusters. So of course, central galaxies of clusters are mostly quenched. I'm showing you star formation rates in the central galaxy versus halo mass, and all the points down here have star formation rate 0. Okay, so 90%, 94% of all these objects are totally quenched, but not all. So some central galaxies, about 5% or so, have non-negligible star formation rates. I'd say actually it can be enormous, right? There can be 1,000 solar masses a year at redshift 0, but it's a very rare phenomenon, right? Perhaps short time scale. If you see these little white X's on top of some of the dots, so these X's are actually marking clusters which are cool cores in terms of the thermodynamic properties of their intercluster medium. So as you might expect, the majority of the clusters with highly star-forming central galaxies are in fact in a cool core state. Okay, so cool cores versus not cool cores, right? This is a statement about the cooling time, for example, in the very center, so within 1% of R500. So what I'm showing you here is a function of halo mass. So this is the simulation data points. And what we see in TG cluster is this diversity, right? There's really no trend with halo mass in terms of the typical cooling times. That's the median. It's basically flat. But at any mass, we see a huge diversity, a factor of 100. So we see at any halo mass, non-cool core systems where the cooling time is larger than the age of the universe. Right? So these are very hot. And we see strong cool core systems where the cooling time is very short. The density is very high, the cooling is very effective. And in the simulations, this is as you can get a sense of it, just a continuum, right? So the non-cool core systems and the strong cool core systems are simply the two edges of the distribution. Right? There's not two distinct populations. That's at least the answer from the simulations. But what's interesting though is that the cool core state of the center of the cluster is directly connected to kind of the global thermodynamical properties of the intercluster medium. So this is the density profiles and entropy profiles of clusters split right into the three types. So the strong cool cores in purple has, as you would expect, right, the highest densities, especially in the center, the steepest entropy profiles and the lowest entropy. The non-cool cores are relatively less dense with flatter, higher entropy values. But the center state of the cluster is really connected to the global properties all the way out to about half of R500. Which means somehow that the star formation in the center, and not just the star formation, then also the ability of the AGN to accrete, and thus the ability of the AGN to release feedback energy, is somehow regulated and connected to the state, right, of the intercluster medium itself, and its whether or not it's in a cool core state. Okay, that's the AGN feedback. I want to go there just to kind of end a bit. So it's not clear, right, how important AGN feedback is in the context of clusters. We have images like this. So this is the observed image of Perseus. This is X-ray surface brightness with some fancy gradient technique applied. So you see all these ripples and waves moving out, possibly driven by AGN feedback. When we make similar images from the simulations, right, we mock the X-ray emission, we do the same kind of gradient technique, we see actually very similar morphological features, spherical rings emerging, and we can definitively say in the simulations that these are driven by AGN feedback events. We've also started to look quantitatively at the properties of X-ray cavities and X-ray bubbles in the centers of clusters. So these are, again, X-ray emission maps showing you kind of the diversity of things you see in the simulation. Cavities which are attached, double cavities rising away from the AGN, bright edges. And indeed, so this is work by Marine Prunier. She started to quantify the occurrence and the properties of these X-ray bubbles and X-ray cavities in clusters compared to imaging data from Chandra. So this is simply a kind of a demographics. This is the fraction of clusters that have either 0, 1, 2, 3, or 4 cavities that would be visible in mock Chandra images versus real Chandra data. So the simulations are these brighter bars underneath, and the data are these colored bars in the background. So there's kind of some rough agreement, but it's also more interesting to look over here. So now we're just looking at clusters that have cavities, so one or more cavities. And the data is the outer ring, and the simulations are the inner ring. And you can start to see, for example, some issues, right? Some tension, some hints towards the physics. So the majority of observed clusters, if they have a cavity, they have two. As you might expect, AGM feedback being kind of a bipolar phenomena. But in the simulation, in fact, that's not how our AGM feedback works. It's simpler. It doesn't need to have two events. You can have one event at a time, so we have this kind of excess of the clusters with only one visible cavity. Okay, I think it's a nice example of how detailed morphological information from something like the X-ray emission can start to constrain the physics of AGM feedback. This is again analysis of the X-ray cavities in these clusters. So we're looking at the area, so the size of these cavities as a function of the distance they are away from the central supermassive black hole. So the observations are in gray, the simulations are in orange. They both follow actually extremely similar trends. So as bubbles are further away, they're larger. Right? So this is reflecting the injection mechanism, and the fact these bubbles, after they've been filled with energy, tend to buoyantly rise in the atmospheres of clusters and move further out, getting larger as they do so. We also looked at this classic relation right between the power you would infer from such a cavity versus the cooling luminosity. So this is this classic debate. Does AGM feedback, as evidenced by these cavities, does it have enough energy to offset cooling, right, to stop the cooling flow, to solve the cooling flow problem? And the reference line here would be the orange line for a relativistic gas. This is the data, and the white, it's scattered around a kind of one-to-one line in some sense. And the simulations are also, right? So it seems to suggest that both in the observations and in simulations that somehow the AGM feedback has energetics roughly sufficient to balance the cooling in these massive clusters at redshift 0. Okay, another very interesting morphological feature we see in these clusters, this is modeling of the radio synchrotron emission done by Wonky, so we'll talk tomorrow, but not about this. And so this is one halo viewed from 3 different angles. On the top, you see radio emission. And from some directions, this object looks a bit like a radio halo, while from other directions, you see a quite symmetric radio relic feature, right? So very cool modeling. I think these are the relics again on top of the X-ray and the total matter contours at the bottom. This is one example. And again, when you start to look at the population across all the clusters, you see a zoo of features, which I think is really cool. So you see double relic features, but you also see these inverted cases. You see single relics. Yeah, so really a diversity. And you can use the cosmological statistics, right, across the few hundred of halos to start to ask how common are these things? When do you expect to see them? You can ask, for example, what fraction of halos have such a relic feature as a function of mass for different luminosity thresholds. Of course, they're much more common in more massive clusters, as they have maybe more frequent redshift merger events. You can also ask something like, how does the luminosity depend on the size, right, of the largest linear size of the relics? We have the observations in squares and all the simulations in circles, and see here the observations are kind of an upper envelope for the simulations, but there's all these little low luminosity things down here, right? So the simulations would suggest that the current radio data is not sensitive enough to see lots and lots of small, low luminosity relics, as you might expect. So that modeling is possible because we're doing the magnetic fields in these simulations, right? So the magnetic fields at redshift 0 in these clusters have strengths which are of the order microgauss to maybe 10 microgauss. They're slightly stronger in more massive clusters. But something quite cool I thought what we found is that there's a lot more information in the magnetic fields in these clusters. So this is work from Katrin Lele, a PhD student in the group. So these are images of magnetic field strength on the scale of R500. No, maybe 10% of R500. Quite zoomed in, are the white circles. So magnetic fields are strong in the center. They decline rapidly as you go further away, but there's lots of structure. They're very tangled, right? They also are really connected to the cool core state of the cluster. So these are profiles of magnetic field strength as a function of distance, split again into strong cool core versus non-cool core clusters. And we see in cool core clusters that we have higher densities, then we naturally have stronger amplification of the magnetic field and higher magnetic field strengths in the center. Okay, but even more interesting than that, is that cool core clusters in particular have a very unique signature of their magnetic fields. So this is an image of magnetic fields in the center of a cluster. This circle is 10% of R500. The color doesn't show you magnetic field strength, it actually shows you magnetic anisotropy, defined the same way you would do for stellar orbits, for example. So if you're at 1, the fields are pointing in the radial direction. If you're black, it's around 0, they're kind of isotropic, and if you're yellow, they're tangential, so they're wrapping around the core. And what we see is that in some clusters, when you go a bit out of the center, the magnetic fields tend to have this preferentially tangential alignment. They tend to wrap around and kind of shield the core. And to keep a long story short, we see this only in cool core clusters. It's pretty cool. So it seems to be particularly the entropy structure of the cool core clusters which allows gravity waves caused by both AGN feedback and inverters to be trapped and thus to realign magnetic fields in this kind of wrapping configuration. Okay, I want to end back onto X-rays for the last 2 or 3 slides. So I think it's a very exciting time for X-ray observations, in particular with respect to kinematics. Right? We have Atomi, now we have CRISM, and we can start to ask the question of how is the hot gas moving for the first time. What we can do is we can take an X-ray emission mock of the simulation, and we can degrade it to match the observational characteristics of something like Atomi. So we can degrade it spatially, and then we can make a photon by photon mock X-ray emission. So a synthetic spectrum in 6 keV or so. These are iron, these are iron lines zoomed in on. So the white data is the actual emission from the simulation, and we then fit that, just as is done in observations, with a model, a broadened line model, that's the blue line. And thus infer the kind of broadening of these lines to make a measurement of the velocity dispersion. The velocity dispersion along the line of sight, so tracing the kinematics of the hot gas. So this is what I'm showing you here on the y-axis as a function of, think of this as a halo mass proxy. And here's the measurement from Atomi, right? From Perseus. We had just this one measurement of about 150, 200 kilometers per second, kind of a low value. And if we select Perseus-like clusters from the simulation, we make the exact mock, so the exact same measurement. We also find characteristically very low levels of velocity dispersion, low levels of turbulence in the cores of these clusters. It's in fact common in the simulations. So we now have CRISM, right? This is the CRISM result for a coma cluster. So on the left we have the 2 pointings. There's a pointing in the center, an offset pointing. The left, the numbers in the boxes are the bulk velocity along the line of sight. Right, and on the right, the numbers in the boxes are the velocity dispersion, 200 roughly kilometers per second. Okay, and in this paper we actually started to compare this measurement to the simulation. So in coma, right, this is coma, the inference is at very low levels of turbulence, meaning a very low level of non-thermal pressure support, only about 3%, right? Which is similar to the most relaxed cool core clusters. And this is maybe hard for the simulations to achieve. So this is a range from ancient simulations all the way down to TNG cluster. And you see a lot of them have a much higher inferred values for how much support turbulence motions in the gas is providing. But the detail, I think, is that the open circles up here, these are all clusters selected from these simulations, because we couldn't do anything else. In the filled dots, we have only non-relaxed systems, similar to the observation, and only for TNT cluster could we actually match the mass, match the cool core kind of state of coma. And in this case, TNT cluster is actually not far off. I skipped this because Naomi will show this and talk about this tomorrow, and I just want to end on this slide. So this is another multi-cluster comparison of CRISM data. Again, line of sight velocity versus halo mass. And you see white dots here. These are measurements of quite a few clusters from CRISM of the velocity dispersion in the cores of these clusters, compared again to the full TNT cluster sample, characteristically finding these kinds of low levels of turbulence in the cores of the clusters. So it seems to be broadly consistent with the data. And I end on a bit of a puzzle then. We saw AGM feedback in action. We saw it generating these ultra-high velocity outflows. We know it can make outflows at thousands of kilometers per second, can produce these cavities in the centers of clusters. We don't see it, right, at all. So these high velocity AGM-driven outflows seem to be invisible, hiding in this kind of inference of the kinematics in the cores of clusters. Okay, so let me give you a few quick conclusions. Big picture is, of course, that these cosmological simulations are our way to test our models, our way to test lambda CDM. And they are the way to realize our theoretical model so that we can compare structure formation to observations. TNT cluster in particular is a new toy with lots of potential applications, lots of observable connections, and a large sample at relatively high resolution. I talked a bit about cold gas, I talked a bit about magnetic fields, and I talked a bit about X-ray kinematics and AGM feedback. And I just want to end by pointing out that everything I talked about, all the simulations I talked about, including TNT cluster, are public, and that you can go to the website, you can download the data, or you can actually do some analysis online. So if you've never played with this, I encourage you to go take a look and see maybe how it can be useful for your science. Thank you.
Thank you very much. I'm sure there are many questions.
I wonder if you have looked at the morphology of the galaxies in TNT clusters and protoclusters.
The central galaxies or the satellite galaxies?
Both central and satellites.
Well, the short answer is no. It's really quite new. We've done very few looks into the results. We've not looked at the stellar morphologies at all yet, but it would be interesting. I think it's quite hard, right? Just as a general comment, it's quite hard to do morphologies or in general the evolution of the satellite galaxies in such massive clusters. Right? We're really starved for resolution in terms of resolving some process like morphological transition of a small satellite galaxy embedded in such a big cluster. It's still quite a challenge. So I'd say we're doing it not really that well, given the resolutions that we can achieve.
So how can you actually hide the agent jet to keep the sigma small?
That's a question, so I think it's interesting to ask.
What is your view?
How could we find such a motion if it's there, first of all? And then, of course, why is such a statistic, a line of sight broadening, not sensitive to this gas? And I think one of the answers is, of course, that although AGM feedback, at least in these simulations, is active at redshift 0 and it produces very high velocity flows, it's not moving much mass. Right? So these outflows are really tracer populations of the gas, and the bulk of the X-ray emitting gas is moving at slower velocity. So perhaps in the CRISM data you could find it, but it would be a small signature somehow.
Thank you for your talk. So I have two short questions. The first one is at the beginning you showed the halo mass as a function of redshift for the galaxy clusters, and I saw there are some systems that the mass actually increase and then decrease. I'm curious about what's the mechanism that causes this fluctuation of the halo mass.
I think maybe you'll debate this later. If you want to measure M200C, right, this is the amount of mass contained in a certain radius, a spherical overdensity measurement. If you have a big merger or something, that can go up, and then it can go back down if a lot of mass goes away. So I think the dynamics of these systems are such that actually mass contained within R200 or something can wave around. It's kind of interesting.
And the second question is you show the X-ray luminosity and the halo mass relation, and from simulation you can see there are some scattering. So I'm curious about what's the physical mechanism driving the scattering.
Yeah, I think the scatter so the main driver of the scatter is, of course, where is it? Is, of course, central density. By far the density in the center is the dominant factor contributing to the integrated X-ray luminosity. I'd say the scatter is similar to the data, perhaps with the exception that we have some of these quite extreme outliers upwards. So I would say that it suggests that some of our strongest cool core systems reach maybe too high densities at some moments in time, and they get really high X-ray luminosities. At least there are no data points from these samples, kind of up there. So maybe that's again a hint that the AGM feedback is too slow, or not working quite the right way to disrupt these cool cores fast enough. I think clusters probably go like that, but maybe the time scales are off. So I think it's interesting implications, of course, for the AGN feedback model.
Hi, thank you for the talk. In your first slide, I'm just curious that you put different simulations that you mentioned, like this a dichotomy in the color, but in illustrations sounds like the peak was in the other direction. Can you tell me what is?
Yeah, so this was one, what you're pointing out here is that the red distribution doesn't really look like the white distribution. This, in fact, is one of the grand failures of Illustris. I would say without any doubt, this rules out this model. Right? So this, in fact, is one of the prime motivations to develop the second generation model, which is called TNG, right? Where we see much better, even quantitatively, the dichotomy in the colors. And in the original Illustris simulation, right, this is much older, it was very hard to generate sufficient red population of quenched galaxies. Right? And the main change here is related to how the AGN feedback is working.
Okay, so then the question is how do you start to fix it, the max, for example, for the black holes in your simulation? I mean, the minimum mass when you start to evolve, and then, well, you have feedback and everything. How do you fix it? What is the initial mass?
Of course, a lot of the aspects of the supermassive black holes are quite simple in these models, including the formation. So the formation, the seeding in these simulations is quite simple. Whenever a halo grows above a certain mass, it gets a black hole at the center. And this black hole starts at a particular seed mass. So these are two parameters. They have maybe a physical meaning, but they're almost free parameters, in the sense that they're representing, the true astrophysical seeding process, which is going to be happening at higher redshift and at much lower mass, and this is simply unresolved in a large volume cosmological simulation. So we have to mimic it by saying that once a halo has grown to a certain mass, it should have had a black hole which has grown to a certain mass, and that's where we start to follow things. So, in fact, I would say those two parameters, a long time ago, were certainly adjusted to fit observations, such as the AGN luminosity functions or the black hole stellar mass relation or Gorian relations kinds of observational constraints.
Okay, thank you.
Thank you for your talk. So, in cocoa clusters, the hot gas will cool down due to thermal instability. But when it cools to around 10 to 4 kelvins, the cooling time scales is even shorter. So it may be lower than the smallest time scale in the TNG simulations. So how did TNG solve this problem?
It's a good question. So I think you've touched on several limitations of the models and the simulations all at once. You've touched on resolution, mass resolution, time resolution, and physics limitations. So first of all, in all of these simulations, which is a common feature of all the large volume simulations, the temperature minimum is effectively 10 to the 4. So cooling processes below 10 to the 4 are not modeled. There's no reason to, because we don't have the resolution to capture cooling in dense gas at those temperatures in effect. So gas doesn't cool below 10 to the 4. So if there would be cooler gas in reality, say molecular gas, that in the simulation will be represented as a component of the 10 to the 4 gas. It'll get kind of stuck at 10 to the 4. And whether or not we can resolve thermal instability in different regimes, I think is a more detailed question, which you would have to look at kind of when and where it happens. But we do see it happening in these simulations, also in the clusters. Right? So we can see, for example, periods where the hot ICM in the centers of the cluster spontaneously cools and forms little clouds, and these fall to the center form a bit of a disk, ignite some star formation, some AGN feedback, which then disrupts the cool gas in the center. So this, when I showed these star-forming central galaxies, and when we have these AGN feedback events, this is a very kind of quasi-episodic process in this model. So it happens, but then it's kind of self-regulating. But the instigation is that, of course, the hot gas in the core gets dense enough that processes like thermal instability, maybe not exactly classical thermal instability, can let cool gas condense in the center.
Maybe last question. Way back. Thank you. Very fantastic talk. Just a quick follow-up question to the supermassive black hole. Yeah, the mass of the black hole come from baryon or dark matter?
So in this model, black holes only grow through the accretion of baryons. They do not accrete dark matter, if that's what you're asking. Yeah, that would be an interesting model to try to see what it would do if they could accrete dark matter.
Short question.
Really quick.
Yes.
So you said that protocluster has a lot of H1 gas associated with that, and but it will eventually be ionized, right? And so, yeah, can you basically update the Dekel diagram from your simulations where the accretion mode is changed?
Dekel diagram?
Yeah, Dekel diagram. Yes.
I think the Dekel diagram in the world of simulators is very debated.
Okay.
First of all, but I think it would be very interesting to update it, yeah, to see what halo mass is and in what condition. First of all, you conform the hot halo, because I don't think it's simply 10 to the 12. I think it's more complicated. And then, you know, the question of when you can have cold streams or cold flows, this is a classic debate. I think, and it's, again, a very difficult problem from the world of the numerical hydrodynamics. It's very hard to actually capture well the interaction of these cold streams and the hot gas in the simulation sense. So I think some of this is open questions, and some of this is kind of the current debate.
Okay.
On the simulators.
Thanks.
Okay, on this note, let's thank Dylan again